So thanks, Stefan, for being here to give this talk. So we're going to go for maybe around 40 minutes. Okay. Mm-hmm. Great. So go for it. Thank you.
Thank you very much. Thank you for inviting me here. I really have great memories about my stay at Simon's last year. It's a pity that we cannot make this reunion there, but I hope I will meet all of you at some other occasion soon when all this craziness with COVID is over. So I'm going to talk about a recent paper on plasma that I have together with Grzegorz Fabiański, Sebastian Faust, and Siavash Ryahi. The paper was recently accepted to the Innovations in Theoretical Computer Science conference. So I'm going to tell you a little bit first, like give you some rather long introduction about what this thing is, like what plasma is, but I will also have some time to describe our technical contribution. So the starting point is the following observation that you probably have seen many times, even today, that blockchains don't scale well, right? So this is because large-scale consensus for long messages is expensive. Okay? So if you have lots of messages and you have many parties, then I mean, there are different definitions of what blockchain is, but one thing that all blockchains have in common is that they need to have a consensus, and this is typically expensive. So there are some solutions to this problem. One is to work on better consensus algorithms. Another one is called sharding. I will not go into this. And the last one, which is particularly relevant for us today, is off-chain protocols. They are also called second layer solutions. And main idea there is that we want to use blockchain as a judge or a notary in real life. So we want to contact blockchain only if we really have to. Main approaches are off-chain channels. This is what Clara was talking about 3 hours ago. And I'm not going to talk about this. And second approach is plasma, or another newer name is commit chains. This will be our focus today. And in a nutshell, what we do is we initiate study of lower bounds or impossibility results in this area. Okay, so before I go to the description of plasma, let me give you some general remarks about how you can view blockchain as a timestamping service, because this is relevant to how plasma works. So one way to look at blockchain is that it's a public timestamping service, right? This is sometimes people, when they describe blockchain to someone, they first like try to explain it by giving some analogs to timestamping, and it's a public timestamping service, meaning that everything that appears there is public. What does it mean exactly, the timestamping service? So the first thing is that it gives the ability to a user to prove that he knew some message M at some time T. Okay, so I can timestamp something on the blockchain, and then maybe 1 year later I can say, okay, I knew this thing already at time T because I signed this. Okay? And that's on a timestamp on the blockchain. By the way, messages are often called transactions, and I will use these two terms interchangeably. And moreover, the second point is stronger, namely that M is publicly available at time T. Okay? So you have these two requirements. One is that simply I want to have a proof that I knew some message. Another one is that I want to prove that I also made this message public. Okay? This is also called data availability, this problem, okay? Because as it will turn out soon, proving that I knew some message is not the same as proving that the message was published. So how does it look like in the most naive view? You have some user and she has a long message M, can be potentially long, and puts this message on the blockchain, and this is the timestamp, right? That this message was there. Actually, people use blockchain for this purpose. Okay, so there's a natural idea to relax these requirements a bit, and maybe say, okay, we only care about proving the knowledge of M. We don't care about proving that M was publicly available. Then we could optimize timestamping in the following way. What we could do is, whenever I want to stamp a long message M, I would just apply a hash function to it and put h of M on the blockchain, right? It's kind of an obvious idea, because then I can later prove to everyone that I knew this message at the given time, but just by showing the message and pointing to where it was, where its hash appeared on the blockchain, right? And this thing can be optimized even further. So if you have many users, say here we have 5 users, but it can be much more, and they each of them has a message mi, then what they can do is they can choose one operator, send messages to this operator. The operator would concatenate all messages into one message M and send M back to the users, and at the same time send a hash of this message M to the blockchain. Okay? So there are these two things, right? The operator needs to hash the message and send it to the blockchain, and then also needs to provide back to the users the entire message M, right? Because they want to be able to verify, to prove later that their hash was included, right? Of course, it can be optimized with Merkle hashing. You can do it in a logarithmic way and without sending message M to everyone, just logarithmic path, right? Okay, call this message hash and timestamp. It's my own name, not standard, just for the purpose of this talk. Okay, a natural question now is what can go wrong if the operator is malicious? So he may not publish the hash, right? But this is like obvious to everyone that he is misbehaving if he's not publishing the hash when he promised to do so. Publish some hash but not include some MIs, right? This is still not so bad, because this means like if I'm a user, okay, I know that my message MI was not included, but yeah, I should just take some other actions. It's like, you know, an attack on liveness. And the last thing that he can do is he may not explain HM. Okay, by explaining HM, I mean he may not provide M to the user. So here on this slide, he would not send this message M. Okay. So and this is precisely what's called data unavailability, right? That some hash was not explained. And the protocol for timestamping would simply work in this case like this. Every user constantly monitors the blockchain and monitors what the operator does. And if something doesn't work, like if, for example, hash was not published or maybe was not explained, then the user will just say, okay, this things with this operator didn't work. I'm going to do it myself, and he himself publishes the hash, right? So you have these two scenarios, optimistic and pessimistic. The optimistic one is that if the operator is honest, then everything goes smoothly, and then this method saves a lot of blockchain space. And the pessimistic scenario, where the operator is dishonest, but then still nothing really bad happens, because the only price compared to not using this service at all is that, you know, maybe I wasted some time trying to convince the operator to publish, to include my message, but yeah, in the worst case, I do it just myself. So we have this weak version of timestamping, like proving that the message was existed at a given time, and it's cheaper but weaker security guarantees. And the stronger version that says not only that the message was known at time t, but also it was publicly available. And the differences are, of course, that the first one is cheaper than the other one, but then this gives you more security guarantees. So a natural question is that maybe for some applications, this weaker guarantees would suffice, right? So for example, in academia, we kind of use this idea of timestamping to claim priority of the results, right? And then what is typically assumed is that you need to make your paper completely public, right? If you want to claim the priority. This is to encourage people to publish, actually, right? So if you could just publish hashes of your papers, and then 10 years later claim, okay, maybe I invented some great thing 10 years ago that became published now by someone, then it doesn't really prove anything, right? I mean, that was my choice not to publish this. But it still provides some information, right? So if I have a hash of my beautiful idea, say PDF, somewhere published on the blockchain, then later I can at least prove that this idea was not stolen from someone, right? And then the question is, maybe we could emulate this strong timestamping using the weak ones, right? And the focus of this work and the focus of Plasma is kind of addressing this problem in the cryptocurrency problem, in the cryptocurrency context. And therefore, we will use terms like transaction fees to describe that something costs on the blockchain, like publishing messages on the blockchain costs. Okay, so this brings us to Plasma. Are there any questions? Okay, this was like kind of simple remarks about timestamping, right? I mean, basically everything on this talk will be simple, hopefully. Okay, so the main idea of Plasma is to apply this hash and timestamp trick to the ledgers. Okay? This was introduced by Poon and Buterin 3 years ago. And the main idea is, again, we will have an operator who will have his own private ledger L. And he will publish L off-chain, for example, on his web page. And periodically, for example, once an hour, he will publish the hash of L on the main chain, so the Ethereum blockchain, in a smart contract. Okay, so there will be the special Plasma ledger that will be maintained by the operator, made off-chain available to everyone, and committed or a timestamp on the blockchain from time to time. So what is this Plasma ledger? There are different flavors of this, but let's say the users own tokens. These tokens can be exchangeable with coins or some other tokens on the real blockchain, on the main chain. And every user can exit Plasma ledger at any time. So if I had some tokens on Plasma ledger, I can always leave the ledger with my tokens. So for example, at the beginning, the user deposits some tokens on the main chain. Then some time passes and the user can withdraw maybe some other amount of tokens on the main chain if some transactions happen. So one way to look at this is that it's kind of like a virtual bank. By virtual bank, I mean that, okay, say in this case we have 3 parties, and say everybody has some amount of coins in the bank. So Alice has 5 and so on. And then if Alice wants to send money to Bob, say 1 coin to Bob, then the operator will subtract 1 coin from Alice's account and add to Bob's account. So Alice's account decreased and Bob's account increased by 1. And of course, the problem is that it all becomes sort of official when the operator publishes his next commitment, his next timestamp on the blockchain, right? So finality here is not great, but the saving is in the blockchain fees. Right? So what are these periodic commitments again? So also we can call them timestamps. So we have operator and smart contract, and simply the following happens, right? So from time to time, say 1 hour, each 1 hour, the operator hashes the ledger and publishes the hash on in the smart contract. Okay, so how does it look like? So suppose we have users and transactions, and there is the operator. And yes, the operator gets gets the transactions T1 up to T5 from the users and computes ledger LI, so the new version of his ledger from the previous one and the new transactions, and sends it back to the users. Again, this LI can be published simply on the web page of the operator. And then at the same time, hash of this new ledger is also published on the blockchain, on the main chain. Right? And the users need to constantly monitor situation and react if if something happens. Should be here. Okay? Main challenge is, of course, handling data unavailability, right? So this is what happens when the operator is nice, but he may also be malicious and do some bad things. And in particular, the hardest thing to handle is what if the operator does not explain hash, okay? So I know that something was hashed. I don't even know if my own message was hashed there. And I don't know what was there at all. Like, I don't know what were the other transactions. Yet I know that the operator did something. Okay? So this is this data unavailability problem. And the main features of Plasma are that as long as the operator is honest, Plasma provides huge savings on transaction fees. Dishonest operator cannot steal money. If there is a conflict between the user and the operator, then they can always use smart contract to resolve the dispute. And again, it's important that every user constantly observes what happens on the blockchain and on the web page of the operator to see if everything is explained and everything is okay. Okay, so this was proposed 3 years ago, and soon after this, there were many variants of this Plasma. This is a picture from, like, I think 2 years ago. So that's far from being complete. I think some projects here are already abandoned. There are other new projects, and yeah, some academic work renames Plasma to commit chains. So it's like commit chains are the whole family of those, and then you have different types of plasmas or maybe other names. The main two types of plasmas are plasma cache, when tokens are independent entities. So there are tokens in the system, and each token has some owner, and that's limited but simpler and easier to implement. And then you have fungible plasma. There are other names like Plasma MVP, NOCUST. I think StarkDEX is also a version of this, where users have accounts where they can have some number of tokens. It looks almost the same, but there are important differences between these two. Yes, so Plasma Cache has a strange property that tokens cannot be divided or merged. They are not non-fungible, that's how they call it. Think of them as game items, so maybe a sword or an armor or whatever, some items from a game. And in fact, one of the first implementations of this Plasma Cache came from the gaming industry. So how does ledger in Plasma Cache look like? You have n tokens. Tokens have some identifiers, say from 1 to n. There are m users in the system, just to simplify things and assume that the set of users is constant. And ledger describes to whom a given token belongs, right? So where bottom means that the token was withdrawn. So for each token I will have some user who is the owner or the token was withdrawn. Right? There is one drawback though. So this thing has the following problem, that if I have k coins or k tokens, and I want to exit this Plasma, then I need to communicate omega of k bits to the blockchain. Right? So if I had 1,000 tokens, then I need to kind of withdraw each of them separately. That's why also you cannot do things like say, okay, let's say 1 Satoshi is a token, right? The smallest possible value in the system, because then it would mean like normally you would have huge transactions. Okay, fungible plasma is better. It's also called Plasma MVP or minimal viable plasma. Again, NOCUST and StarkDEX. So tokens can be divided and merged arbitrarily. And the Plasma ledger simply defines, as usually in the bank, just users and their accounts, right? So you have user U1 has X1 tokens, U2 has X2 tokens, and so on. Right? So this is like a standard bank. Yes, and think of it as real numbers. Of course, in reality we have finite precision, but And then it's much better because to exit with k coins, you need to just communicate all of log k bits. So exiting even with large amounts is efficient. So you have these two types of plasma. I haven't told you how they work, and I have no time to do it. So you have to trust me they exist. Plasma cache has large exit size, pessimistically. Fungible plasma has short exit size. So this column looks like plasma, fungible plasma is better, but there is a second column which uses a term that I will explain in a moment. So this term is non-uniquely attributable mass exits, and non-uniquely attributable mass exits don't exist in plasma cache, but are a problem in fungible plasma. Okay, so there is a trade-off. There is a certain problem that fungible plasma has that plasma cache doesn't have. I will explain it in a moment. Okay, so again, what if there is a data unavailability? So if the operator didn't explain a given hash, so what fungible plasma does is, okay, so here's the situation where, say, there was Li was explained, still Li plus 1 is not explained. So I don't know Li plus 1. Then what fungible plasma tells the users, just exit plasma as soon as you can. Take your money and run. Something is wrong. And this doesn't exist in plasma cache. Plasma cache doesn't have this problem. Like, even if you see that something is wrong, you don't need to immediately escape. Why this is a problem? Yeah, so first of all, if the operator really disappears and stops explaining his hashes, then every honest user has to do it. So every honest user has to escape from the blockchain immediately. This can cause congestion on the blockchain, and therefore you need long timeouts for this. Okay? And this is a problem because typically you don't want to have very long timeouts. I mean, they were, like, last time I checked, they were saying like 2 weeks, for example. Okay? And moreover, this whole thing is non-uniquely attributable, which I will explain in a moment, but basically it means the data unavailability is subjective. So I can claim that data is unavailable. Ale can claim that actually data is available. And from the point of view of blockchain, it's impossible to prove for each of us who is right and who is wrong. So what are these uniquely versus non-uniquely attributable faults? So uniquely attributable faults are a situation where smart contract knows which party is responsible for a problem. This has several advantages. One of them is that you can say, okay, every user will put a deposit aside, and if we see that he is cheating, we'll penalize him, and this penalty will come will be used to cover the fees, for example, right? Or to compensate some other loss, even loss of time. So examples of uniquely attributable fault is that the party doesn't send some message to a smart contract, or signs to contradictory statements. Non-uniquely attributable faults are a different situation, where a smart contract knows that some party is not following the protocol, but he doesn't know which one. So this is precisely this problem when, for example, I'm sending a message to Ale, and I'm claiming I did it, and Ale claims it hasn't arrived. And this is a problem because it also leads to this phenomenon called griefing. The problem comes from the fact that it's not clear who should pay the fees for resolving the conflict. Natural approach is, if we have a conflict, so for example, if I was supposed to send a message to Ale and we have a conflict, if this happened, then we'll go do it via blockchain, right? So I will now, Ale complains about me to the smart contract, and the smart contract explicitly asks me to send the message, right? Then there are non-trivial transaction fees, and then we say, okay, we split them 50-50. Of course, this is a problem because this may still not prevent some users from misbehaving. For example, if I want to destroy my competition and I'm richer than my competition, it may be okay for me to pay 50-50. And this is called griefing. I think this term comes from like computer games. I can grief someone. It will cost me, but it will also cost him. Yes, Vitalik was writing some papers about this. And there is a real life situation observed in a system called Funfair that actually in such situations, honest users often prefer not to fight on the blockchain, right? So this is some kind of a channel system. In this channel system, if I have a conflict with someone, I should go on the blockchain and try to resolve it, but it costs so much that it makes no sense for me to do it. And of course, then the other party knows that I will have no incentive to do it, so it's actually incentivized to maybe apply this attack, and this creates problems. Okay, so again, what is the difference? Plasma cache and fungible plasma, exit size large, short, but here non-uniquely attributable mass exits, and here problem with of non-uniquely attributable mass exits. Okay, so if the operator stops explaining his hashes, then everybody has to quickly run. And the question is it inherent? So can we have a plasma that has short exit size and no mass exit at the same time? One reason why one may think about that it is the case is that plasma cache is simpler to describe and simpler to implement. So this is an obvious advantage. So maybe people were actually doing this plasma cache thing only because it's simpler, not because it has some inherent advantages over plasma MVP, which is harder to implement. Okay, and this is the question that we address in the paper. Okay, so some terminology. When I say attack on plasma, I mean a strategy for the adversary who corrupts some users and for the environment to tell the honest users what to do. And mass action of size alpha is a situation where the honest users need to quickly send messages of total length at least alpha to the smart contract, even if they were not instructed to exit, right? Because if we allow, if we don't write this, then we would have a problem because, of course, the environment can simply tell everyone to exit, and then, of course, always mass action can be caused. Why do I need to use the term mass action instead of mass exit? That's because it can be the case that, I mean, mass exit kind of means that you exit the whole chain, and mass action means that you just have to interact with the blockchain. Maybe you still stay within the same smart contract with your token, but it's just pushed on some safe account. This is a technicality. And our results simplified are that there exists, for every plasma system pi with M users, there exists an attack on plasma that causes non-uniquely attributable mass action of size m quarter with significant probability, or there exists an attack that causes an exit size of an honest user to be at least m over 4, again with significant probability. Okay? So I can do these two things. Either I can make, if you give me plasma, then either I can make this attack, so this is like this plasma MVP problem, right? That I can either cause that there will be a mass exit, or I can I will not have this problem, but I will pay in the sense that large exits from honest users may be large. There's a caveat here. We have an additional assumption that so according to our definition of plasma, the users don't communicate with themselves. They communicate just with the operator. Okay, so what are the implications of this? Again, this is the copied from the previous slide. So suppose plasma, we have a plasma with no non-uniquely attributable mass exit actions of any size, then, or a large size, then 1 doesn't hold, right? Therefore 2 has to hold. Sorry, this alpha is not needed here. And this means that plasma needs to have exits of size M4. Right? And the other way to look at this, okay, so suppose this doesn't hold, so it's only short exits, then 1 has to hold, so I need to have mass exits of a large size. Okay, so let me, in the remaining few minutes, let me tell you about how the proof works. So the proof, as I mean, it's usually, I think, the case with like lower bounds that some even very intuitive things need a lot of work if you want to make them formal. So we make it all formal in the paper. Just let me tell you what is the main intuition. Okay, so we have users. We have user U1 who will play a special role, and the operator. Okay? And at the beginning, each user has his own token. Right? The operator has no tokens, but otherwise everybody has a token. And then we choose a random set S, which is a subset of these guys, right? So these are guys from U2 up to UN, and I choose a random set S. So this is the set S, and these are the remaining users. And what these users do is they are these users from set S transfer all their coins to user U1. And then user U1 immediately exits with these coins. Okay, so since the set is random, then kind of like around half of the coins or half of the tokens disappeared now. This is the first thing that happens from a random set S. Okay? And the operator is nice to these guys. Okay? So he's talking to them, no data unavailability. He's also talking to U1. He's ignoring these guys. Okay? So he's launching a data unavailability attack on them. Okay, and then there is a second phase. So we have again the set S and all the remaining users. And now these users really turn malicious, and they start to pretend that they actually haven't transferred these coins. Okay, so this is done by some kind of rewinding of machines. They say, okay, I will now pretend I'm a good guy and I haven't transferred my coin before. Okay? And then we say, okay, let all the users exit the plasma chain. Yeah? So these users exit plasma chain. They are honest users instructed by the environment, and these are users who are malicious users who are pretending they haven't transferred their coins. And the problem, of course, is that if any of these guys manages to exit, then we have broken plasma. It's not that we made some like non-uniquely attributable fault. We just broke plasma completely, because this means if one of those exited with his token, then there will be not enough tokens left for the good guys to exit. Right? So at least one of them loses money. So it's very important now that the honest users would actually convince the smart contract what is the set S. Right? So they need to go to the smart contract and convince what is the set S. Right? And the intuition, of course, you should be much more careful in the real proof, but the intuition is that in order to convince a smart contract about the situation, like who exited, the smart contract needs to know the set S in advance, so after phase one. Because otherwise there is no way to prove who is actually lying and who is honest. So we have two options. Either in this, so this is again the first phase. Either the users from the set in the first phase from the set U2 UM minus S, either all of them said, okay, there is data unavailability. We need to do large communication to the blockchain to kind of let ourselves be heard that we complained about data unavailability, right? Or, and this is a non-uniquely attributable mass action because, again, data unavailability is subjective. Or this guy in this phase one, when he exits, he needs to put long information on the blockchain so that S can be reconstructed from this. Okay. So we are using the fact that maybe I should have said it earlier. We are using the fact that if you want to have a description of a random subset of M elements, then you need kind of M bits for this. Okay, so formal proof is in the paper. The conclusion is that there is a good example. Plasma is a good example for the difference between weak and strong timestamping. So for Plasma cache, it's different than from Plasma MVP. And another conclusion is that there are good theoretical reasons why actually people were working on 2 types of plasmas, not one. So this simply depends on what is more important for you, if you care more about short exits or more about data availability problem. I think Ale knows more than me about StarkDEX. Last time I checked, you had something like data availability committee there, right? If you so you have like a special. So this is kind of like a trick to bypass this problem, that you assume that you have some committee with honest majority that votes about if data was available or not. Of course, this is a solution, but it kind of changes the model. So kind of this result shows that it's in general unavoidable, unless you give up on some assumptions that we made. And yes, the practical community, especially these Ethereum people, they are working, at least 1 year ago, they were talking a lot about rollups or ZK rollups. So they were kind of like a way to solve this data availability problem in yet another way. That was 1 year ago. I don't know what happens now with this, because somehow often they change focus. But I think ZK rollups are actually implemented.
Aren't the ZK rollups just kind of this fungible plasma? I mean, it's basically it's. Go ahead.
I think in as far as I understand rollups, there is this way that you actually make this data available for a moment on the blockchain. All data is available. So like you have miners certifying that this data was available, and then simply it disappears from kind of like the state of the contract. I mean, you have this difference between like light clients and full nodes. And I think full nodes will always store it, but light nodes will not.
Okay, so like I think of rollups as basically the mechanism of proving a batch of transactions, but then kind of whether the batch of transactions is reflected in some data on the blockchain or not, it's kind of some sort of orthogonal property. But yeah, like typically they're understood to be like with data on chain.
Yes.
Not
yes.
Yeah.
I think the technical trick is that they put it as inputs to the function call, and the inputs are not stored forever. I mean, not like by the light node.
But anyway, that's like I mean, it doesn't lead to like to scalability. I mean, it's primarily like mitigate.
Yeah. Okay, that was it. Questions?
Cool. Thank you.
Thank you.